Hello warriors, this is Miss Lemons and this is the final video that I'll be making about calorimetry. This time we'll be going over one practice problem of a calorimetry experiment. If you need more help after this practice walkthrough, please reach out to me so that I can help walk you through another practice problem if you so choose. So this practice problem correlates with number 4 on your notes. So number 4 says, a 300-gram piece of iron was heated to 87.5 degrees Celsius and placed in a calorimeter that contained 123 grams of water at 10 degrees Celsius. The final temperature of the iron and the water was 60.5 degrees Celsius. Calculate the specific heat of iron. The specific heat for water is 4.184 joules per gram degree Celsius. Woof. This is a lot of information. So it's really important that we are color coding and marking up what all of our values are so that we don't mix up anything. The first thing that we need to do is determine our system and our surroundings. So just for simplicity's sake, I always like to make water my surroundings and iron, or the object, to be my system. You can flip-flop it if you like, but again, I think it makes a little more sense to see that the water is surrounding the iron, therefore iron the system, water the surroundings. Okay, now we're going to go ahead and fill out as much of this chart as possible by using the numbers from word problem. How we can do this is using the units as a way of identifying which number belongs to which variable. You also have to pay attention to what the context clues of the word problem are. So you can figure out if this is the mass for the system or the mass for the surroundings. So it says a 300-gram piece of iron. So we know that this is mass of iron. It was heated to 87.5 degrees Celsius. So 87.5 degrees Celsius, that is our initial temperature for the iron. The iron was then placed in a calorimeter that contained 123 grams of water, which is our surroundings. So I have the mass of our surroundings at 10 degrees Celsius. So we have the initial temperature of the water. The final temperature of the iron and the water was 60.5 degrees Celsius. So they both have the same exact temperature because they reached thermal equilibrium and they're occupying the same space. Just so you guys know, the final temperature of the system and the surroundings will always be the same value. And that's because the system and surroundings have reached thermal equilibrium, therefore have the same temperature. Then you're going to calculate the specific heat of iron. So we don't know what C is for the system. And we are given the specific heat of water, which is 4.184 joules per gram degree Celsius. Okay, so I went ahead and I just picked apart that word problem and filled in as much table as I could. Now I'm going to go ahead and calculate delta T for both the system and the surroundings using delta T equals T final minus T initial. So for our setups for the surroundings and the system, our system is going to be 60.5 degrees Celsius minus 87.5 degrees Celsius, whereas the surroundings is going to be 60.5 degrees Celsius minus 10 degrees Celsius. So our final answers here, the delta T of the surroundings would be 50.5 degrees Celsius, and then delta T of the system would be negative 27 degrees Celsius. Please pay attention to your signs. We're not always subtracting the biggest number from the smallest number. You have to pay attention to your variables, which is why this chart can be so helpful. Because if we know that this is our final temperature and our initial temperature, we're not going to be flip-flopping them too much in our calculations. So yes, you can have a negative change in temperature. If you get a negative number, make sure you write the negative in your table. So now that we've calculated delta T for both the system and the surroundings, we're going to go ahead and plug in the values for the system or surroundings into Q equals MCAT and solve for Q. If you take a look at the values that we're given, we actually don't have enough information to calculate for Q for the system. We don't know the specific heat of the system. That's what we're trying to figure out. So we can't calculate Q for the system. Instead, we do have enough information for Q of the surroundings, the water. So we're going to plug in these values here into Q equals MCAT to solve for Q of the surroundings. So Q of the surroundings, this is what your setup should look like, equals 123 grams times 4.184 joules per gram degree Celsius times 50.5 degrees Celsius. When we multiply those numbers together, I get 25,988.916 joules. That is my final answer, or my Q of the surroundings, my heat of the surroundings. So I plug that into my table. Now I'm going to use loco E to figure out the amount of heat the system/surroundings absorbed or released. Loco E tells us that the Q of the system plus the Q of the surroundings gives us a net movement of heat of 0. Plug in what we know, and that's Q of the system plus 25,988.916 joules equals 0. In order to get Q of the system by itself, we have to subtract both sides, subtract 25,988.916 from both sides. So our final answer ends up being negative 25,988.916 joules. Now, guys, I do want to point out here the fact that our system has a negative temperature change and a negative Q is not a coincidence. If you have a negative change of temperature, you will have a negative Q. If you have a positive change of temperature, you will have a positive heat value. Okay, also, the Q of the system is always going to be the opposite sign of Q of the surroundings. Always. If one object loses heat, the other object has to gain that heat. So it makes sense that we have one positive value and one negative value. So after we figured out the Q of the system, we're going to plug our values for system or surroundings into Q equals MCAT and solve for C. We've already solved for everything for the surroundings, so we're going to be doing this for Q of the system. So Q of the system equals MC delta T. That would be negative 25,988.916 joules equals 300 grams times X, because we don't know what X is, times negative 27 degrees Celsius. Now, it's really important that you include those negatives in there, folks, and there is a special number button on your calculator. You don't use subtraction symbol. If you look at your 9 numbers, it's right underneath the number 3. That is how you do a negative sign instead of doing the subtraction sign. So you're going to plug in those values and make sure you have your negatives in place. When you plug them in, you end up getting a rounded number of 3.21 joules per gram degrees Celsius for the specific heat of iron. Now, folks, really quick, if you end up with a negative specific heat, or for instance, a negative mass, that is not possible. You cannot have a negative specific heat or a negative mass. That is not possible. If you do end up with a negative number for either one of those variables, you have done something incorrect in your calculation. Perhaps you forgot to put a negative number in your calculator. Perhaps you forgot to put negatives on one of your 2 numbers in your setup. But you cannot have a negative number for specific heat or for mass. That is my walkthrough for question number 4. If you need additional practice problems to be walked through, please join me and your peers during one of the Google Meets or view one of the previous Google Meet video sessions. I also have a few videos on the YouTube channel of other practice problems from other scientists or other teachers. So good luck, and if you have any questions, you know you can always reach out to me.